Imagine a place in space where gravity reigns supreme, a place where the very fabric of space and time is twisted and contorted by an immense force. This is not a scene from a science fiction movie, but a reality in our universe. A place so dense, so massive, that nothing, not even light, can escape its grasp. These regions of space are known as black holes, and they are among the most mysterious and fascinating objects in the cosmos. This is a black hole, a cosmic abyss that devours everything in its path. They are formed when massive stars collapse under their own gravity, creating a point of infinite density known as a singularity. These enigmatic objects are the ultimate cosmic vacuum cleaners, relentlessly sucking in matter and energy from their surroundings. The material that gets too close is drawn into a swirling vortex, spiraling down into the black hole. But what happens to objects that venture too close to these gravitational behemoths? As they approach the event horizon, the point of no return, they experience extreme gravitational forces. As an object approaches a black hole, it encounters a force unlike anything else in the universe. The gravitational pull becomes so strong that it warps space and time around it, creating a phenomenon known as gravitational lensing. The immense gravitational pull of the black hole stretches and squeezes the object, distorting its shape in a process known as spaghettification. This term vividly describes how objects are stretched into long, thin shapes, much like spaghetti. This intriguing phenomenon is a testament to the extraordinary power of gravity and the bizarre nature of black holes. The closer an object gets to the singularity, the more extreme the stretching becomes, until it is ultimately torn apart. In this journey, we will delve into the heart of black holes, exploring their properties, their types, and the fascinating phenomenon of spaghettification. From stellar mass black holes to supermassive ones at the centers of galaxies, each type has its own unique characteristics. Through vivid descriptions and compelling examples, we will unravel the mysteries of these cosmic wonders and gain a deeper appreciation for the awe-inspiring forces that govern our universe. We will look at how black holes influence their surroundings and the role they play in the evolution of galaxies. So, fasten your seatbelts and prepare for a thrilling ride as we embark on an exploration of the spaghettification effect, a journey to the very edge of reality. We will also discuss the latest discoveries and theories in black hole research, shedding light on these dark giants. Join me, and let us unlock the secrets of these celestial monsters together. By understanding black holes, we not only learn about the universe but also about the fundamental laws of physics that govern everything around us. Black holes are not empty spaces as their name might suggest. Instead, they are some of the most fascinating and mysterious objects in the universe, captivating the imagination of scientists and the public alike. They are regions of space-time where gravity is so strong that nothing, not even light, can escape their pull. This immense gravitational force warps the fabric of space-time itself, creating a phenomenon that has intrigued physicists for decades. This incredible gravitational pull arises from the collapse of massive stars at the end of their life cycle. When these stars exhaust their nuclear fuel, they can no longer support themselves against the force of gravity. Imagine a star, much more massive than our Sun, running out of fuel. As it burns through its nuclear reserves, the outward pressure that once balanced gravity diminishes. As the outward pressure from nuclear fusion weakens, gravity takes over, causing the star's core to collapse in on itself. This collapse happens in a matter of seconds, leading to a dramatic and violent event. This collapse compresses the star's mass into an infinitely small point called a singularity. The density at this point is so extreme that the laws of physics as we know them cease to function normally. The singularity lies at the heart of a black hole, hidden behind a boundary known as the event horizon. This boundary is not a physical surface but rather a point beyond which nothing can return. The event horizon marks the point of no return, beyond which the gravitational pull is so strong that escape is impossible. It is this boundary that gives black holes their name, as no light or information can escape from within. Anything that crosses the event horizon, be it a spaceship, a planet, or even light itself, is doomed to be consumed by the black hole. The fate of these objects is sealed as they spiral inward, drawn inexorably towards the singularity. Black holes are like cosmic vacuum cleaners, relentlessly sucking in matter and energy from their surroundings. This process forms an accretion disk of material that spirals into the black hole, heating up and emitting intense radiation. But unlike their household counterparts, Black holes do not simply collect matter, they devour it, adding to their already immense mass and gravitational pull. This consumption can lead to the growth of supermassive black holes, which reside at the centers of galaxies. This insatiable appetite makes black holes one of the most powerful and enigmatic objects in the universe. Their study not only helps us understand the life cycles of stars, but also the fundamental nature of gravity and space-time itself. Black holes come in different sizes, much like stars. These enigmatic objects are scattered throughout the universe, each with its own unique characteristics and mysteries. From the smallest to the largest, black holes captivate the imagination of scientists and enthusiasts alike. Astronomers classify them into three main categories based on their mass: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Each category represents a different stage in the cosmic life cycle and offers insights into the dynamic processes that shape our universe. Stellar mass black holes are the most common type, formed from the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse, leading to the formation of a black hole. This dramatic end of a star's life is a spectacular event, often accompanied by a supernova explosion. They typically have masses a few times that of our Sun, but are squeezed into a region only a few miles across. This incredible density means that the gravitational pull of a stellar mass black hole is immensely strong, warping space and time around it. Imagine the entire mass of a star crammed into a space the size of a city. This mind-boggling compression results in a gravitational field so intense that not even light can escape its grasp, rendering the black hole invisible to direct observation. Intermediate mass black holes are rarer and, as their name suggests, fall between stellar mass and supermassive black holes in terms of mass. These elusive objects are a key piece in understanding the growth and evolution of black holes over cosmic time. They can have masses hundreds to thousands of times that of our Sun, and are thought to form from the merger of smaller black holes. This process of merging is a violent and energetic event, releasing gravitational waves that ripple through the fabric of spacetime. Supermassive black holes are the true titans of the cosmos, lurking at the centers of most galaxies, including our own Milky Way. These colossal entities have a profound impact on their host galaxies, influencing star formation and the overall structure of the galaxy. These behemoths can have masses millions or even billions of times that of our Sun, and are thought to play a crucial role in the formation and evolution of galaxies. Their immense gravitational pull can shape the orbits of stars and even affect the distribution of matter within the galaxy. Each type of black hole, from the smallest stellar mass black hole to the largest supermassive black hole, exerts its own gravitational influence on its surroundings. This influence can lead to fascinating phenomena such as the bending of light, known as gravitational lensing, and the acceleration of particles to near-light speeds. And it is within this gravitational grasp that the bizarre and fascinating phenomenon of spaghettification takes place. As objects venture too close to a black hole, they are stretched and compressed in a process that vividly illustrates the extreme nature of these cosmic giants. Spaghettification, a term coined to describe the extreme stretching and compression of objects as they approach a black hole, is a testament to the extraordinary power of gravity. This phenomenon occurs due to the immense difference in gravitational pull between the object's nearest and farthest points from the black hole. Imagine a spaceship unfortunate enough to venture too close to a black hole. As the spaceship approaches the black hole, the gravitational pull on the front of the spaceship becomes significantly stronger than the pull on the back. This difference in gravitational force stretches the spaceship in the direction of the black hole, like pulling on a piece of chewing gum. Simultaneously, the sides of the spaceship experience a compressive force, squeezing it inwards. This combination of stretching and squeezing elongates the spaceship, distorting its shape into a long, thin strand resembling a noodle, hence the term spaghettification. The closer the spaceship gets to the black hole, the more extreme the spaghettification effect becomes. Eventually, the stretching and squeezing forces become so intense that they overcome the spaceship's structural integrity, tearing it apart into a stream of atoms and particles, ultimately consumed by the black hole.